Okay, next I want to talk about polyprotic acids. And these are acids that have more than one acidic proton. They have more than one hydrogen ion that can come off. Okay? Sulfuric acid is an example. It's a diprotic acid. It can lose 2 protons. So first, we lose the first one. It transfers the hydrogen ion to the water to form the hydronium ion and leaves this here. But this is an acid anion. So this itself is still an acid. Now, sulfuric acid is a strong acid, so that's why we just used a single arrow to indicate that it's a strong electrolyte, and it's just completely dissociating into this. But the HSO4 is weak, okay? So now we're going to use a double arrow. So there is no Ka value for sulfuric acid because it's a strong acid, but there is a Ka value for the hydrogen sulfate ion. It's a weak acid. It only partially dissociates. It only partially gives up some of its hydrogen to water to form the hydronium ion and leaving behind the conjugate base. Okay. So again, the first one's strong. The second one's weak. So in a molecular equation, it would look like this, but in the complete ionic equation, it's going to look like this. Okay. It's going to be shown as dissociated. This guy, on the other hand, it's going to look like this in the molecular equation, and it's also going to look like this in the complete ionic equation because it's a weak acid, a weak electrolyte. We only dissociate strong electrolytes. Okay, so here is another example. Sorry, bugs. Here is another example. Here is oxalic acid. And oxalic acid, again, is another diprotic acid, but in this case, both of the acidic protons are weak. So it'll lose its first. Again, it's going to transfer hydrogen to water to form the hydronium ion, leaving behind the hydrogen oxalate. And it has a Ka value of 6.0 times 10 to the negative 2. We're going to call that Ka1. Then we have this, which is going to be an even weaker acid. Okay, and they always get weaker. We'll talk about that again towards the end of this chapter too. So as we get a negative charge build up, well, that negative charge is going to attract the hydrogen ion that's trying to leave. So it's making it harder for it to leave. Okay, so again, here would be the second one. Again, it's going to donate its proton to water to form the hydronium ion and then leave behind the conjugate base, which is just the oxalate ion. And we're going to call it Ka2 for the second ionization. And we see that its value is 6.1 times 10 to the negative 5. So it is 3 orders of magnitude, 10 to the third. It's 1,000 times weaker than the first acidic proton. Okay, so this is going to be another thing too. If we want to determine the pH of a solution of oxalic acid, we only ever have to look at the first ionization because the second one's always going to be orders of magnitude weaker. And so it's not going to increase the hydronium ion concentration enough to change the hydronium ion concentration from the first one to any number of significant digits. Okay, so we're always going to be able to use just the first acid to calculate the pH. We will be doing that kind of stuff, okay? So again, they get weaker as they go along. And there are triprotic acids like phosphoric acid. There are tetraprotic acids out there. For example, EDTA, ethylene diamine tetraacetate, okay, EDTA, actually has 4 acidic protons. And there's even acids out there that have hundreds, okay? So again, we could have many polyprotic acids. Okay, so, and again, in each case, the acid equilibrium constant expression is just the concentration of our products, each raised to the coefficient, divided by the concentration of our reactants raised to the coefficient. So just, again, just like in chapter 15, these equilibrium constant expressions, in this case, the acid ionization dissociation expression, are going to be the same as we've always seen before. Okay, so in general, again, the second ionization constant for a polyprotic acid is much smaller, generally orders of magnitude smaller than the first ionization constant. And we're just going to call them Ka1, Ka2, Ka3, Ka4, however many it has. So again, we can see that phosphoric acid is what we call a triprotic acid. It has 3 acidic protons. Okay, and again, the Ka values get smaller and smaller and smaller as we go down the line. Okay, let's try an example. So ascorbic acid, which is vitamin C, is a diprotic acid, so it has 2 acidic protons. And we want to know what is the pH of a 0.25 molar solution. And then we want to know what is the concentration of the ascorbate ion. So that means we lose both of these, and the ascorbate ion would be this -2, right? So we want to know what is the pH, and then we want to know what is the actual ascorbate ion concentration. So to deal with the pH, like I said, we only have to deal with the first loss of the hydrogen ion, right? So we're going to look up the Ka values, both of them in this case, for the ascorbic acid. So there's the Ka1, and we can see that the Ka2 is much, 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 much weaker, 7 orders of magnitude, 10 to the 7, right? So that's 100 million times weaker than the first. Okay, so again, like I said, the pH can be determined by simply looking at the first Ka, because this one's so small, it's not increasing the hydrogen ion concentration within our uncertainty. So we looked up both of our Kas. We're going to set up an ice table now. Again, this is just looking for the first one, so we have the first dissociation. Our initial concentration was 0.25 molar. Again, we're going to assume that the hydrogen ion concentration is 0, and we had pure water, so there was none of the hydrogen ascorbate ion in it to begin with. We're going to lose our reactant, so -1x. We're going to gain our product, so +1x and +1x. At equilibrium, we just add the 2 values together. Our equilibrium constant expression will be our products, each raised to the first, since the coefficients are 1, divided by our ascorbic acid raised to the first. We now plug in our equilibrium concentrations and our Ka value, which is 8.0 times 10 to the negative 5. Again, I don't want to have to solve the quadratic formula, so I'm going to take the initial concentration divided by the Ka value, and if that's greater than 1,000, we'll be able to ignore this -x term, okay? So 0.25 divided by 8.0 times 10 to the negative 5th is 3,000. That is greater than 100, so we're going to be able to ignore the -x term, okay? We can ignore the -x term. That now simplifies to this, and all I did is I rearranged it, right? I took this and I multiplied it to this side, and now I'm going to take the square root to get rid of this. I'm just going to take the square root of both sides, and that gives us a hydrogen ion concentration of 0.00447. So to get the pH, right? So again, remember that X is the hydronium ion concentration. So to get the pH, we'll just take the negative log of that. That gives us a pH of 2.35. Well, that makes sense. It's less than 7, so it means it's acidic. Okay. Okay, now we want to get the ascorbate ion. So now we're going to have to use this one here, right? So we've already dissociated. We got some of this in solution. And now it's going to react with water to transfer its proton to the water to form hydronium and leaving behind the ascorbate anion. So we're going to have to set up another ice table. This time we're going to do it in terms of y instead of x. But I just changed variables because it's a different ice table. And we're going to use our Ka2 in this whole thing. Because this, again, this is the Ka2. This is the second loss of a hydrogen. So there's our ice table. Now this time, our initial concentrations are going to be determined from the equilibrium concentrations of our first ice table. So this initial concentration was X from our first ice table, which we determined to be 0.00447. The same thing is true for the hydronium ion. It's not 0 anymore. That's going to be the equilibrium concentration from our first ice table, which again was the 0.00447. right? These were the products of our first ice table. Now, we are going to assume that there was no ascorbate ion already in solution. We're going to lose our reactant, so minus 1x, 1y. We're going to gain our product, so plus 1y and plus 1y. Equilibrium, we just add the initial and the change for each one of them. We're going to set up our equilibrium constant expression. Now, we're going to assume, so this is something we're going to do in the next chapter. We're not going to be able to use, the only time you could use that assumption Ca over Ka, or later on we're going to see Cb over Kb, is when we were dealing with the first ionization of a weak acid or a weak base. If there's more than, if it's minus more than 1x, let's say it's minus 3x, that assumption won't work anymore. If we have both a minus x and a minus x and a minus or plus y term, plus x term, we can't use that ratio anymore. It won't work. But we can say this is really, really tiny. And we know when these values are tiny, we could ignore the minus y term. Now, normally we would check that with the assumption. But we're going to assume that this is so small compared to this number here that we're going to be able to ignore the minus y term. And in the same way, we're going to be able to ignore the plus y term. Now, we're going to come back and we're going to check this assumption. You've got to check the assumption. So I'll be looking for that on an exam. Did you check the assumption? Okay. So we're going to start off by ignoring both the plus and the minus y terms, not the independent y, but the plus and the minus y terms. Well, that now shows me that this cancels this, right? And so that means the concentration of the free ascorbate ion in solution was actually simply equal to the Ka value. Now, we do have to check our assumption. So I'm going to take this value and I'm going to plug it back in. Okay. And when I plug this back in, if I get the number back to the correct number of sig figs without it changing, which I do, right? Because this is 10 to the negative 12. It's way, 0, 0, 0, 0, 0. It's way out there. So this number is the same. So our assumption is correct. So again, I need to see this check. That when I take this and I either add it or subtract it, right? We ignored a plus and a minus. But if one works, the other one's going to work. Okay, so you only got to check one of them. You don't got to check both of them. So again, if I add this together and this number doesn't change from its original value to the correct number of sig figs, then our assumption was correct. Our assumption was allowable. Okay. Okay, so any questions on that so far? Okay, so the important take home here then, when you have a polyprotic ion, the concentration of the completely deprotonated ion is simply going to be the Ka value. It's going to be the Ka2. Or if it's triprotic, the concentration, for example, of phosphate is just going to be whatever the Ka3 value is. Okay, so that's the important take home here. So if you know that, and I ask you what the concentration of this is on an exam, you could just say it's the Ka value. You don't have to go through all of the work that I just showed you. Again, do your homework. Okay? Do your homework and you'll be aware of these shortcuts. Okay, again, any questions on the polyprotic stuff?